by the hydrolysis of SiF4 or SiCl4. SiCl4 or SiF on hydrolysis gives H4SiO4 called as orthosilicic acid. Now in this case, under the byproduct HCl here and here H2SiF6. Why not H2SiCl6? Why we are getting only HCl? But in the case of SiF4, in place of HF, we are getting H2SiF6. 1 point. So SiF6 2 minus, SiCl6 2 minus. So this is octahedral structure. Steric factor nana. Silicon surrounded by 6 fluorines, small size fluorines, whereas silicon surrounded by 6 large size fluorines. So here we have repulsions between large size fluorine atoms. Steric factor, steric effect. That's why SiCl6 2 minus does not exist. Only SiF6 2 minus exists. That's why byproduct is HCl here in the case of SiCl4, and in the case of SiF4, byproduct is H2SiF6. It is called as hexafluorosilicic acid. And this orthosilicic acid on strong heating undergoes dehydration and gives SiO2, silicon dioxide. This means important on this method, particularly the reactions. SiCl4 on hydrolysis gives H4SiO4 plus HCl, whereas SiF4 on hydrolysis gives H4SiO4 and H2SiF6. Whereas in the case of HCl, H2SiCl6 does not exist due to steric factor. Now let us move to a few properties. Some properties. It is insoluble in water. It dissolves to a small extent when heated under high pressure. Generally insoluble in water. With carbon, very useful reaction. When silica is heated with carbon in an electric furnace, it is reduced to, please highlight this compound, SiC, carborundum we call it as. Chemically called silicon carbide. The silicon carbide structure is similar to diamond nana, polymeric structure. In diamond we have carbon-carbon linkages. In silicon carbide, alternatively silicon carbons are available. Very hard material and very good abrasive also. Mainly abrasive means for cutting as well as drilling hard materials, we are using another hard materials. Diamond is good abrasive. Silicon carbide also good abrasive. Very useful compound is obtained when SiO2 is heated with carbon in an electric furnace. Then SiO2 is reduced to silicon carbide, commercially called as carborundum. Not corundum nana. Corundum is Al2O3. This is carborundum, chemical name silicon carbide as SiC. One more useful reaction. When heated to 1600 degrees centigrade, silica melts to form one type of glass called as quartz glass. Red hot quartz glass, when plunged into water, does not break into pieces. Due to this nature, it is used in making optical instruments. This is the nature of quartz glass. Mainly for making optical instruments, we are using this quartz glass. Next property, with alkalis, gives silicates. Na2SiO3. This Na2SiO3 called as water glass. That Na2SiO3 we are using to prepare another type of glass called as water glass, quartz glass. Next with metal oxides. With metal oxides, it form once again silicates, sodium oxide, sodium silicate, calcium oxide, calcium silicate with carbonates. Once again gives silicates because carbonates are there, no? They liberates carbon dioxide gas also. So sodium carbonate SiO2, sodium silicate plus CO2, calcium carbonate plus SiO2, calcium silicate plus CO2. So all these reactions, reactions with carbonates, reaction with metal oxides, reaction with alkalis, all these three reactions supports the acidic character of SiO2. With alkalis, with metal oxides, with the metal carbonates, corresponding silicates are formed. This is another useful reaction. SiO2 dissolves in HF due to the formation of H2SiF6. So SiO2 with HF gives SiF4 and dissolves in HF and form a soluble hexafluorosilicic acid. Similar to this, we are expecting reaction with HCl, HBr, HI. But SiCl62 minus, SiBr62 minus, SiI62 minus does not exist due to steric factor. That's why SiO2 dissolves in HF due to formation of H2SiF6. Because this reaction, mainly this hydrogen fluoride, very useful compound for etching on glass surface. Etching on glass surface means making designs on the glass surface. We are adding HF. Glass means SiO2 only, no. So by adding HF, glass dissolves. Then we can make our desired design on the glass surface. Etching on glass surface with the help of HF, mainly due to formation of soluble hexafluorosilicic acid, octahedral SiF6 2 minus ion. Similar to this, SiCl62 minus, SiBr62 minus, Si62 minus does not exist on the basis of steric factors. That's why the only compound which dissolves SiO2 is HF. And uses used as a building material in the form of sand, used as an acidic flux in metallurgy. Flux means to remove gangue particles. Gangue particles means impurities, earthy impurities. Gangue plus flux gives rise to slag. Because SiO2 acidic, no, it is called like acidic flux in metallurgy, mainly for removing basic gangue. If gangue is acidic, then we have to add basic flux. Best one is CaO, calcium oxide. Next, bricks made up of a mixture of powdered sand, clay, and the lime. Three chemicals I am highlighting here. Powdered sand, clay, and the lime. With the help of all these three, we are preparing some type of bricks here. They are always used for lining the furnace, used in the manufacturing of steel. Because different furnaces we are using, in those furnaces, we are maintaining very high temperatures. In some cases, under those high temperatures, there is a chance to damage the furnace. That's why we have to protect the furnace. For protecting the furnace, the inner part of the furnace lined with some hard melting high melting solids. Refractory materials we call them as. Refractory materials, high melting solids, they can withstand to high temperatures and protect the furnace by lining the furnace with such type of refractory materials. So powdered sand means SiO2, clay, lime, all these mixtures, bricks we are using for lining the furnace. And one more, we have another application of SiO2. One variety of SiO2 is called quartz. It is one of the important allotropic form of SiO2. It is one of the important crystalline form of SiO2, quartz. We have colored varieties and we have transparent varieties. Colored varieties used as gems in jewelry, and Transparent variety used for the manufacturing of lenses, optical instruments, etc. Mainly colored quartz we are using in jewelry in the form of different types of gems. Now I am giving different forms of silica. First one is crystalline form, quartz, tridymite, and cristobalite. And quartz is colorless when pure, but the presence of impurities impart color to the crystal. And quartz, tridymite, cristobalite at low temperature. Now we have alpha forms as well as beta forms. Alpha quartz, beta quartz, alpha tridymite, beta tridymite, alpha cristobalite, beta cristobalite. Alpha forms are stable, are important at low temperatures, and beta forms are important at high temperatures. But out of all these, the purest form of silica is quartz, also called as rock crystal. And these crystalline forms, quartzite, tridymite, cristobalite, these crystalline forms are interconvertible at different temperatures. Because low temperatures alpha form, high temperatures beta forms, and you can convert one form to another form by changing the temperature. This is the flow chart. Alpha quartz, alpha tridymite, alpha cristobalite, beta quartz, beta tridymite, beta cristobalite. So low temperature, high temperature. And finally, at around 1740 degrees centigrade, it melts nana, and we are getting a liquid form of silica. It is equal to the melting point of SiO2. So like this, we can convert these crystalline forms of SiO2 from one temperature to another temperature. Then one form is converted to another form, interconvertible forms. And we have another type of quartz, crushed form of quartz. We call it as sand. For building purpose we are using. And sand particles with iron oxide, we call them as sandstone. And amorphous forms of silica. Just now I told crystalline forms, quartz, tridymite, cristobalite. Now we have some amorphous forms also, agate, onyx, and jasper. And flint is one type of glass nana. It consisting of amorphous silica associated with quartz, flint. One more type of SiO2 we have called as kieselguhr. This kieselguhr is nothing but siliceous rock composed of the remains of minute sea organisms. From sea organisms, from those sea organisms, some waste comes out. That waste contains some sort of siliceous rock. That siliceous rock is called as kieselguhr. These two, please put important, flint as well as kieselguhr. Flint consisting of amorphous silica associated with quartz, and kieselguhr consisting of, it is one type of siliceous rock composed of the waste that is coming out from remains of minute sea organisms under the sea water. These are the different forms of SiO2, mainly crystalline form and amorphous form. Crystalline form, quartzite, tridymite, cristobalite, and amorphous form, agate, jasper, onyx. And these crystalline forms are interconvertible, and one alpha form is converted into another beta form by changing the temperature. Next we are going to the important concept of silicon, silicones. These silicones are organosilicon compounds containing SiO(Si) and SiC linkages. Silicones are called as organosilicon polymers, organosilicon compounds containing SiO(Si) and SiC linkages. Two types of linkages it contains. Silicon oxygen silicon as well as silicon carbon linkage. Both are available. Before going to silicones, one point I am writing here is SiH4.
I found this on the web.
Is called as silane. SiH4 is called as silane. SiCl4 tetrachlorosilane, CH3SiCl3 methyl trichlorosilane, CH3 taken twice SiCl2 dimethyl dichlorosilane, CH3 taken thrice SiCl trimethyl chlorosilane. This is written as RSiCl3. This is R2SiCl2. This is R3SiCl. Alkyl, dialkyl, trialkyl chlorosilane. Or alkyl or aryl group also possible. But my discussion is limited to alkyl group. And these silicones containing SiO, Si and SiC linkages are prepared by the hydrolysis and condensation polymerization of organosilicon halides, mainly chlorides. Condensation polymerization means polymerization takes place with the loss of H2O. Then it is called condensation polymerization. Hydrolysis followed by condensation polymerization. So why polymerization takes place between molecules? Why not within the molecule? Generally, if we have carbon, if we have OH group, so elimination of water takes place, then we are getting a compound like this. Similarly, I am taking silicon, okay, I am putting OH here, then similar to previous case, elimination of water, then Si and Si, double bond O I am writing, but this is wrong. Silicon unable to form effective p-pi bonding with oxygen. So this group is called a ketone group. Similar to ketone, we are unable to prepare Si double bond O linkage compound. So instead of removal of water molecule within the molecule, we can remove water molecule between molecules. Between molecules means, for example, I am taking here Si, OH, okay, plus HO, Si. Now removal of water. SiO, Si. Now this is condensation polymerization. So instead of removing water molecule in one molecule of silicon compound, it is better to remove water molecule between two or more number of molecules. That is called as condensation polymerization. But names are given silicones. Silicones means looks like ketones, but bondings are entirely different. In ketones we have C double bond O groups. In silicones, such type of Si double bond O linkages are not possible because of less ability of forming p-pi multiple bonds between silicon and oxygen. So these silicones are prepared by the hydrolysis and condensation polymerization of organosilicon halides, mainly chlorides. So how can you prepare organosilicon halides? I mentioned here. Organosilicon chlorides are prepared by, you have to take SiCl4, that SiCl4 reacts with the Grignard's reagent, RMGX, R is alkyl or aryl group, but my discussion is limited to alkyl. So I am taking CH3MgCl, then we are getting CH3SiCl3, CH3 taken twice SiCl2, CH3 taken thrice SiCl, RSiCl3, R2SiCl2, R3SiCl type of organosilicon chlorides are prepared by the reaction between SiCl4 and Grignard's reagent. One more method we have, same SiCl4, it reacts with CH3Li, methyl lithium, or Li, alkyl lithium or aryl lithium. Then also we can prepare CH3SiCl3 type or SiCl3 here, R2SiCl2, and here R3SiCl uptime. And one more method, a specific method called as Rocho process. Rocho process. In this Rocho process, we are preparing R2SiCl2, only this type of organosilicon halide, by the reaction of 2 moles of methyl chloride with silicon by using copper catalyst at 300 degrees centigrade. And fourth method, methyl chloride, hydrochloric acid and silicon, copper catalyst, heating to 300 degrees centigrade. Then we are preparing CH3SiCl3 type organosilicon halide, means RSiCl3. Previously R2SiCl2. Previously any type R2, R3 by using first two methods, SiCl4 with Grignard's reagent, SiCl4 with alkyl or aryl lithium. Now let us take alkyl or aryl substituted chlorosilanes. Then hydrolysis. Then we are getting intermediate compound as selenol, similar to alkanols, Nana. Alkanol. Alcohol groups are there, no? Similar to alkanol, here we are getting silicon surrounded by OH groups. We call them as selenols, intermediate compounds. These selenols immediately undergoes condensation polymerization and gives silicones. Alkyl or aryl substituted chlorosilanes, hydrolysis gives selenols. On condensation polymerization, they converted into silicones. Just to mention, no, carbon surrounded by 2 OH groups, elimination of water, yes, this is possible. Silicon surrounded by 2 OH groups, elimination of water, this does not. One point I am writing here, carbon readily form p-pi multiple bonds with itself and with other small sized atoms. Like nitrogen, oxygen, etc. C triple bond NO, C double bond NO, C triple bond O, C double bond O, C double bond C, C triple bond C. Like that, carbon readily form p-pi multiple bonds with itself and with other small sized atoms because of its small size. Silicon unable to form effective p-pi bonding. That's why silicon with oxygen prefers a single covalent bond but not multiple bond. That's the main point for constructing different types of silicones. Now let us move to, but this is the requirement, Nana. Types of silicones. This part is important. First I am taking R3SiCl. What is R3SiCl? Trialkyl chlorosilane. That, like that, please practice, Nana. Trialkyl or triaryl. Mainly trialkyl chlorosilane. Hydrolysis followed by condensation polymerization gives dimeric silicone. These names. So dimeric silicones are formed by dash type of organosilicon chlorides, means trialkyl chlorosilane. See what happened, Nana, here? See R3SiCl first converted into R3SiOH and then dimeric silicone. The first step is hydrolysis. Second step is condensation polymerization. Diagrammatically I am representing like this. R3SiCl gives R3SiOH, no? R3SiOH, 2 molecules I am taking, and let us eliminate H2O. Then we are getting this type of silicone. Silicones means organosilicon compounds containing SiO, and SiC linkages. These are called silicones. R is there? No. So silicon carbon linkage is there. Silicon oxygen silicon linkage is also there. Because two molecules are linked here, this is called as dimeric silicone. If you put CH3 in place of R, we are getting a compound like this. SiO linkage. SiO linkage. It is called hexamethyl disiloxane, official name. Hexamethyl disiloxane. Hexamethyl disiloxane type of dimeric silicone is obtained from dash type of organosilicon chloride, trialkyl chlorosilane, R3SiCl. This is first type of silicone. Dimeric silicones formed by dash type of organosilicon chlorides means R3SiCl, trialkyl chlorosilane. Now I am taking R2SiCl2. This R2SiCl2 dialkyl dichlorosilane. Dialkyl dichlorosilane. Dialkyl dichlorosilane. This dialkyl dichlorosilane hydrolysis followed by condensation polymerization gives linear chain silicones. Also gives cyclic silicones. My name's Nana. Previously dimeric silicone. Now linear chain or cyclic silicones. This R2SiCl2 hydrolysis under carefully controlled conditions can produce cyclic structures with rings containing 3, 4, 5 or 6 silicon atoms. But till now they synthesized silicon rings containing 3, 4, 5 or 6 silicon atoms. These are obtained by carefully controlled conditions. See here. This is one selenol, another selenol, another selenol. Because R2SiCl2, no? R2SiCl2 gives R2SiOH taken twice, which undergoes polymerization. In previous case, we have only one OH group. R3SiCl gives R3SiOH, then elimination of water. Now R2SiCl2 gives R2SiOH taken twice, then elimination of water. Condensation polymerization. Condensation polymerization. Condensation polymerization. Condensation polymerization. And gives a chain silicone, linear chain silicone. SiO linkages. SiO linkages. So many SiO linkages are formed and gives a linear chain silicone structure. Linear chain silicone or straight chain polymer. So R2SiCl2 gives linear chain silicone or straight chain silicone. Now cyclic silicones. See here. 3 molecules I am taking. This is one R2SiOH taken twice. R2SiOH taken twice. R2SiOH taken twice. Then elimination of water. Elimination of water. Condensation polymerization. Then gives a cyclic compound containing 3 silicon atoms. This is the cyclic silicone containing 3 silicon atoms. This is called as tris-cyclo, bulky group, no? Tris-cyclo dialkyl siloxane. Near each silicon, two alkyls are there, no? That's why cyclo dialkyl siloxane. Three compounds are there, so that's why tris. Tris cyclo dialkyl siloxane. Two alkyls, dialkyl siloxane. Similarly, we can prepare one more cyclic compound containing 4 silicon atoms. That's why it is called tetragis. Cyclo dialkyl siloxane. There also each silicon surrounded by 2 alkyl groups. These are the two formed by R2SiCl2 dialkyl dichlorosilanes. Gives linear chain silicons as well as cyclic silicons. This one. Suppose if you want to control the chain length, for controlling the chain length, at the end, suppose we have SiO, like that we have. Okay, but we have to control the chain length. To control the chain length, here we need one end we need all 3 alkyls. Then polymerization stopped there. So this particular part is called as chain controlling unit. Which one, Nana? Having 3 alkyl groups, no? That means R3SiCl, not R2. R3SiCl, very useful unit for controlling the chain length. Depending on the requirement, whenever we have to stop the chain length, we have to add sufficient quantity of R3SiCl. Then the polymerization stopped there. That point I mentioned here. If some CH3 taken thrice SiCl is mixed with R2SiCl2, so R3SiCl is mixed with R2SiCl2 and hydrolyzed, the R3SiCl will block the end of the straight chain produced by R2SiCl2. This R3SiCl block the chain length which is formed by R2SiCl2. That's why this R3SiCl is called as chain stopping unit. Chain stopping unit. One example I mentioned here. This R3SiCl, Nana, first it involves in polymerization by forming R3SiOH, and elimination of water takes place between these two. This is the unit. This is the unit formed from R2SiCl2. This is the unit obtained from R3SiCl. So R3SiCl unit used to stop the chain length formed by R2SiCl2. That's why it is called chain stopping unit. Left side also we can write one more molecule. Then we can control left side also. Both ends are controlled by adding R3SiCl to the reaction mixture containing R2SiCl2. This is the chain length stopped here. Other extension is not possible because of methyl groups here. So once again, R3SiCl gives dimeric silicon, R2SiCl2 gives linear chain silicons as well as cyclic silicons, and the linear chain silicon stopped by adding a suitable quantity of R3SiCl unit to the reaction mixture. Next I am taking RSiCl3. This RSiCl3 called as alkyl trichlorosilane. Alkyl trichlorosilane. Hydrolysis followed by condensation polymerization gives highly stable cross-linked silicons are formed. So many cross links are formed here, not linear chain. In the case of previous example, R2SiCl2, we are getting only linear chain silicon. But in this case, polymeric compound we are getting but we are getting highly polymerized compound. We are getting containing number of cross links. Let's see here. R SiCl3, no? So R SiCl3 means one end is alkyl group. This is alkyl group, and remaining three are OH groups. So here also one alkyl group. So here elimination of water. Here elimination of water. Here elimination of water. Here also elimination of water. Between these two also elimination of water. Like that, number of links are formed here. But top to bottom extension is not possible because alkyl group is there. No, alkyl group is chain blocking unit nana or polymerization stopping unit, and thereby so left to right to bottom left to right to, and one chain above, one chain below. Between these two also links are possible. That's what is called cross linked. This part is called as cross link. This is called as cross link. Cross linking. Cross linking. That's why this is called cross linked silicone. This is the example. Cross linked silicone. Highly polymerized silicones are obtained from RSiCl3 containing two linear chains, and those two linear chains are linked. One more example. Okay, another form. Previously, R I put top here, R I put top here, bottom, bottom. But in the second case, here I am taking R, here I am taking R randomly. Like this also possible. Cross-linked silicones or branched silicones are formed. So at one place I mentioned, Nana, this conclusion is required. R3SiCl gives dimeric silicone, R2SiCl2 gives linear chain silicone or cyclic silicone, RSiCl3 gives cross-linked silicones. What are the applications of these silicones? When we are using these silicones, what is the need of preparing these silicones? First application is, first nature is, they're all strongly water repellent nature, hydrophobic nature, a good electrical insulators, and they have non-stick properties and anti-foaming properties. Their strength and inertness are related to two factors. One is their stable silica-like structure containing SiO-Si linkage, and the SiO bond energy is very high, around 500 kilojoule per mole. In addition to that, SiC bond also strong. SiC bond is strong, SiO bond is strong. Because of this only, silicones are highly stable and highly inert also, and their strength also very, very high because of skeleton structure, 3D structure, chain structure, and strong SiO and SiC bonds. And just now I told silicones are, first point, water repellent. This water repellent nature mainly arises because a silicone chain is surrounded by organic side groups. Because of these organic side groups only, they are all hydrophobic nature, water repellent nature, because of the attachment of organic subgroups around silicons. These silicones, different varieties we have, liquids we have, oils, greases, rubbers, elastomers, resins, so many. Industrially, it is one of the very, very important compound, silicones. And this one more advantage is these are all biocompatible also. That's why in medicine also very useful. By using these silicones, we are preparing number of surgical and cosmetic implants, Nana. Because of that, their dash nature, biocompatible nature. That's why they introduce a silicones part in this chapter. Very, very useful compound, water repellent nature, electrical insulators, oils we have, greases we have, rubbers we have, elastomers, resins we have, and biocompatible nature. That's why these silicones we are using in making surgical and cosmetic implants. These are the few points about silicones. Now we are entering into another very, very important concept called silicates. Now listen carefully. A few points I'm giving here before going to silicates. Quartz, mica, feldspar, zeolites. These are all different types of silicates, Nana. These are all important examples of silicates. But mainly these quartz, mica, feldspar, zeolites, these are all found in almost all rocks, clays, and soils present in earth crust. Means naturally available silicates, Nana. Quartz, mica, feldspar, zeolites, they are all found in almost all rocks, clays, and soils present in earth crust. In addition to that, we have naturally man-made silicates also available. In that, glass as well as cement. Two most important glass cement useful silicates, but these are not available in the earth crust. They are all man-made silicates, glass as well as cement. So now observe here. All silicates have tetrahedral SiO4 4 minus ion. Is a basic building unit. మనకు సిలికోన్స్ సిలికేట్స్ అన్న సిలికాన్ ఆక్సిజన్ కాంపౌండ్స్ సిలికోన్స్ కంటైన్స్ SiO(Si) and SiC linkages, but here in silicates we have the fundamental basic building unit is tetrahedral SiO4 4 minus unit. That SiO4 4 minus, this is the structure SiO4 4 minus. But in this discussion, we are representing like this. దీన్ని మీరు కాన్సన్ట్రేట్ చేయండి. In this structure, how many bonds are there? 3 bonds or 4 bonds are in this structure, highlighted one. 4 bonds are there. Not 3, 4 bonds are there. Where is 4? Where is 4 back side? Okay, this circles are there. No, solid circle is silicon and open circle is oxygen. So 4 open circles are there, no? So 4 oxygen there. This oxygen projected backside. Tetrahedral structure, no? Only 3 oxygens we are representing on the paper and 4th one backside. So 4 bonds are there, not 3 bonds. 4 SiO, Si linkages are available. Now, ఈ స్ట్రక్చర్ మనం డెవలప్ చేసుకుంటాం ఫర్ రిప్రజెంటింగ్ డిఫరెంట్ టైప్స్ ఆఫ్ సిలికేట్స్. ఒక్కసారి చూడండి. Depending on the manner in which different SiO4 units are linked together, silicates have grouped into the following categories. But depending on the linkage, we have different types of silicates. Names, Nana. Orthosilicates, called nesosilicates, pyrosilicates, sorosilicates, disilicates, islands, cyclic silicates, ring silicates. Next, chain silicate. In chain silicate, 2 types are there. Single chain silicate, double chain silicate. Single chain silicates are called pyroxenes. Double chain silicates are called amphiboles. Neso, soro, ring, pyroxenes, amphiboles, single chain, double chain. Next we have sheet silicates. Sheet silicates called as phyllosilicates, PHYLLO, phyllosilicates. Next we have 3-dimensional silicates, 3D silicates. So these are the varieties, 1, 2, 3, 4, 5, 6 varieties. Orthosilicates, pyrosilicates, cyclic silicates, chain silicates, 2 types, pyroxenes, amphimoles, sheet silicates, and 3-dimensional silicates. So construction of the 6 silicates you have to practice. How does SiO4 4 minus units are linked? That part you have to concentrate. One by one, let us see now. Orthosilicates. Orthosilicates, also called as nesosilicate. So orthosilicates, what type of silicates are called orthosilicates? Means containing simple silicates and contain only discrete orthosilicate ions. What is the meaning of discrete orthosilicate ion? No sharing at all. Only one unit is available. That is SiO4 4 minus unit only available. These ions do not share oxygen atoms with one another. Do not share. No sharing. Without sharing, one unit is available. Discrete unit is available. Now onwards, orthosilicate ion means we have to write SiO4 4 minus ion. SiO4 4 minus ion is called as orthosilicate ion. Examples నాన్న మీరు బాగా ప్రాక్టీస్ చేసుకోవాలి. విలిమైట్ ఫార్ములా జాగ్రత్తగా చూసుకోండి. Zn2 SiO4, ఫినసైట్, Be2 SiO4, ఫారెస్టరైట్, Mg2 SiO4. జింక్ +2 కదా నాన్న, బెరీలియం +2, మెగ్నీషియం +2, పాజిటివ్ ఛార్జ్ 4 యూనిట్స్, సో నెగిటివ్ ఛార్జ్ 4 యూనిట్స్, SiO4 4 మైనస్. స్ట్రక్చర్స్ కూడా నేను మెన్షన్ చేశాను. కోఆర్డినేషన్ నెంబర్స్ ఆఫ్ జింక్ అండ్ బెరీలియం 4. Here coordination number of magnesium 6 in forsterite, phenacite, willemite. We have one more variety called as olivine. Has the same structure as forsterite, but about 1/10 of the magnesium ions in forsterite are replaced by Fe+2 ions. This is derivative of forsterite. In forsterite, some of the magnesium ions replaced with ferrous ions. Then we are getting olivine type of orthosilicate. Next we have zircon, zirconium, zirconium SiO4. Coordination number of zirconium here 8. It is one of the important gemstone, zircon, another type of orthosilicate. Please put important this one, zircon, zirconium, 4th B group nana. SiO4 4 minus unit. Next one other type we have garnets, we call them as GARNETS, garnets. These are another type of orthosilicates containing this molecular formula. MM, this 2 and 3 indicates oxidation state. +2 oxidation state metal, +3 oxidation state metal, and SiO4 taken thrice. +2, 3 are there, therefore total positive charge +6. +3, 2 are there, therefore total positive charge +6. So total positive charge 12 units, therefore negative charge 12 units. That's why SiO4 taken thrice means 3 SiO4 4 minus unit. Negative charge is -12. So charges you have to balance nana. Here one few examples I am giving having +2 oxidation state, magnesium, calcium, iron, having 6 coordination number, and +3 oxidation state, iron, chromium, aluminium, having 8 coordination number. Coordination number 8. Mainly nana, these garnets were using to make sandpaper, sandpaper. Smoothness కోసం వాడతాం కదా నాన్న. That paper, sandpaper, is made up of garnets. And in addition to that, large crystals of garnet are cut and polished and used as a red gemstone. One type of garnet, by properly cutting and properly polishing, we can prepare a gemstone having a red color. These are the few points about orthosilicates. So orthosilicate means simple silicates containing a discrete unit. That is important, Nana. Discrete means no sharing of oxygen atoms between SiO4 4 minus. In some cases, Nana, between two units sharing is there. That's why I'm writing do not share. These ions do not share oxygen atoms with one another. Remaining tomorrow will continue on different structures. Cyclic, sheet, okay, linear chain, double chain, and their formula you have to practice. After completing this tomorrow, we are going to carbon oxides. Then we are going to third group oxides. Okay, then tomorrow we'll continue.